Hello everyone, a very good morning all of you. This is Chandra Shekhar welcoming you all to the India's largest, best and your favorite live learning platform, that is BYJU'S Exam. So you guys are watching me live through the another session of Concept Capsule series, and today's session is all about a very important topic of thermal radiation, that is radiation shield. So guys, before I start, let me quickly introduce myself. As most of the students already know about me, but still those who are meeting me for the first time, my name is Chandra Shekhar, Mechanical Engineering graduate, IIT Delhi, and also I have cleared Engineering Services examination. I have worked in SAIL for a couple of years, and from last 9+ years or close to 10+ years, I am into teaching, guiding the students who are preparing for various competitive exams. Whenever you have any doubt, you can always contact me using the mail ID which is mentioned over the screen, and you should also join me on the Telegram. My group is Mechanical by Chandra Shekhar, and the link is also mentioned over the screen. Okay, so back to the topic. Why do we use radiation shield? The shields are generally used to reduce the effect of thermal radiation in high temperature applications like combustion chamber, nuclear reactors, thermal power plants, etc. Mostly aluminum material is used as a radiation shield because it is having very high reflectivity and because of its very low emissivity. Now, how do they reduce the radiation effect? They neither remove any heat from the system nor they include or add any heat to the system. They only place a thermal resistance in the path of the radiation heat flow, and because of the increase in thermal resistance, the rate of heat transfer due to radiation decreases. That is how they work. Even if there is a black shield, there are two types of thermal resistance when we talk about the radiation circuit diagram or electrical analogy of radiation. We discuss about two thermal resistances for radiation. One is the surface resistance due to non-black nature of the surface. Another resistance, thermal resistance, is space resistance due to the space between the surfaces which are exchanging radiation heat. So when there is a black surface, black body, the shield is a black surface, then the surface resistance will be 0 for a black surface. But even though the surface resistance is 0, there is an increase in the space resistance in the path of the heat flow, and because of the increase in the space resistance, there is definitely be reduction in the rate of heat transfer due to thermal radiation. All right. So let us have some mathematical analysis about that. First of all, let us talk about the two non-black surfaces. Let us talk about two non-black surfaces which are exchanging heat with one another. Body 1, which is non-black, body 2. Body 1 is having emissivity epsilon 1, area A1, temperature T1. Body 2 is having epsilon 2 emissivity, area is A2, temperature is T2. Whenever they are having the exchange of heat with each other, then we can analyze it by using the circuit diagram. Because of the non-black nature of the body 1, there is a surface resistance coming into picture, that is R1. R1 is the surface resistance. R1 is the surface resistance. This is R1. 1 minus epsilon 1 upon epsilon 1 A1. Then there is a space resistance between 1 and 2, that is R1 to 2. This is R1 to 2, and the third one is again the surface resistance for body 2. So there are three resistances in series, and Q net can be calculated by Q net is equal to delta EB. This is EB1 minus EB2, that is the thermal potential divided by equivalent thermal resistance. So we can say that is sigma into, according to Stephen Boltzmann law, T1 to the power 4 minus T2 to the power 4 divided by R1 plus R1 to 2 plus R2. That is how we can find out Q net. Now, if there is no change in temperature T1, if there is no change in temperature T2, so we can say Q net is inversely proportional to equivalent thermal resistance. And that is where the concept of radiation shield comes into picture. When we increase the equivalent resistance by introducing a radiation shield, then Q net will definitely decrease. Alright. So this expression, if we apply for large parallel plates without any shield, because they are parallel plates, so self shape factor will be 0. F11 is equal to F22 is equal to 0, and because the plates are very large, can be considered as enclosure. So we can say this is how without shield Q will be equal to delta EB upon R equivalent, that is A1 F122 and epsilon to A2, epsilon 2 into A2. Denominator will be this. We have already discussed about it. Now, for large parallel plates, we can say A1 is equal to A2 is equal to same A. Similarly, F122, because it is enclosure, so according to enclosure theorem, F122 is equal to 1. If we put the values in the expression, A1, A2 can be taken as A only, F122 can be taken as 1, because F121 plus F122 is equal to 1 according to enclosure theorem. Because F121 is 0, so F122 is equal to 1. So our expression will be Q122 is given by this expression. A into sigma, the unit is what? Into T1 to the power 4 minus T2 to the power 4 upon. Now, for epsilon 1 is equal to epsilon 2 is equal to same epsilon, then we can say Q1 to 2 will be equal to sigma into A into T1 to the power 4 minus T2 to the power 4 divided by 2 by epsilon minus 1. If both the surfaces are having same emissivity, then the radiation exchange between the surfaces will be given by this expression. Unit is. Alright. Now, if we introduce one shield, now try to understand. If we introduce one radiation shield, then there will be, earlier there was only one space resistance, now there will be two space resistance. This is shield, which is surface 3. So 1, 3 will be one space resistance, and 3, 2 is the another space resistance. Along with that, because it is a non-black surface, then there will be two surface resistances coming into picture. So earlier there were 3 thermal resistances in total. Now there will be 6 thermal resistance. The first resistance, if we draw the circuit diagram, try to understand here. First surface is a non-black surface, then there will be a surface resistance R1, 1 minus epsilon 1 upon epsilon 1 A1. Then there will be a space resistance between 1 and 3, that is R1 3, 1 upon A1 F1 2 3. Then there is a surface resistance on the left hand side for the shield, that is 1 minus epsilon 3, that is towards side 1 upon epsilon 3 A3, that is R3 towards 1, that is the surface resistance. There is another surface resistance towards the side 2, that is 1 minus epsilon 2 upon epsilon 3 upon epsilon 3 A3, that is R3 again towards side 2. These are the surface resistance. There will be two surface resistance because any non-black body can be treated as a black body with a cover. So due to the cover, there will be surface resistance on the left hand side as well as on the right hand side. Then there will be space resistance between 3 and 2, that is R3 to 2. And finally, there will be a surface resistance for the surface 2, that is R2. All the resistances will be in series, and equivalent resistance will be sum of all the resistances which are shown in the figure. So for one shield, if we analyze, so we can say R equivalent will be R1 plus R1 to 3 plus R3 towards 1 plus R3 towards 2 plus R3 to 2 plus R2. That is R equivalent, and Q1 to 2 is equal to delta E upon R equivalent. If we write all the parameters, then the expression will be like this. This will be the expression. Now, because they are very large parallel plates, so the self-shaped factor will be 0 for the plates, and for the from the enclosure theorem, the shape factor between each and every surfaces will be 1, and A1, A2, A3 will be same for infinitely long parallel plates. So our expression will be reduced. This is the modified expression when A1, A2, A3 can be replaced by A, and the shape factor between 1, 3, 2, 3 are replaced by 1. That is F1 to 2. Now, if you see, generally on the left hand side and on the right hand side, the shield will have the same emissivity. So, if we say epsilon 3 towards side 1 is equal to epsilon 3 towards side 2 is equal to epsilon 3, then our expression will be for one radiation shield, Q1 to 2 will be equal to sigma into A into T1 to the power 4 minus T to the power 4 divided by 1 upon epsilon 1 plus 2 by epsilon 3 plus 1 upon epsilon 2 minus 2 will be our expression. This will be our expression, right? Towards side, left side as well as towards the right side. Now, if we generalize for n radiation shield having the emissivity as epsilon 3, having the emissivity as epsilon 3, then we can say Q for n shield will be given by sigma into A into T1 to the power 4 minus T2 to the power 4. Numerator will remain same. Then the denominator will be 1 upon epsilon 1 plus 2n by epsilon 3 plus 1 upon epsilon 2 minus n plus 1. This will be the expression for n. Getting it? That is how the increase in thermal resistance will reduce the effect of radiation by the introduction of the shield. Now, if epsilon 1 is equal to epsilon 2 is equal to epsilon 3, all the emissivities are same, that is epsilon, then if the emissivity of all the surfaces are equal, then our expression will become like this. Then our expression will be equal. For we already know for epsilon 1 is equal to epsilon 2, Q without shield or no shield, we have already written is equal to sigma into A into T1 to the power 4 minus T to the power 4 upon 2 by epsilon minus 1. For n shield, it will become n plus 1 into this, and Q1 to 2 no shield. This is Q1 to 2 no shield. Finally, what we can say, so what we can say here is Q ratio of Q and shield to Q without shield is given by 1 upon n plus 1, where n is the number of thermal radiation shield, n is the number of shields having same emissivity, as that of the plates. Emissivity, that is epsilon. All right. So that is all for this session. See you in the next session, and we will discuss another topic, another concept. That is all from my side. Thank you guys. Thank you very much. Take care.